Hello everyone, I'm Chris McIntosh. I help teach the statistics courses. I wanted to go over a few things about descriptive statistics to emphasize a little more for this week's material. Descriptive statistics refer to summarizing, organizing, and presenting data. If we want people to understand our data quickly, we don't just present them with the raw data, like the example you see on the left side of the slide. We often summarize it for them, like the example you see in the middle of this slide. In the example, it's easy to see we have 9 females coded using 0 and 11 males coded using 1. We can often convey meaning even more quickly by presenting data as a figure, as you can see on the right side of the slide. It's easy to see that males on average are taller than females for the sample provided. The way we summarize and present data depends on the level of measurement. Categorical variables, nominal and ordinal, are usually summarized using frequencies, that are counts, and percentages. Categorical variables are usually displayed as a figure using bar charts. Continuous variables, interval and ratio, are usually summarized using measures of central tendency and spread. Continuous variables close to a normal distribution are usually summarized using the mean as the measure of central tendency and the standard deviation as the spread. Continuous variables that have a skewed distribution with outliers are usually best summarized using the median as the measure of central tendency and the range as the spread. If the mean and the median differ by much, it's probably best to use the median. Continuous variables are usually displayed as a figure using histograms and box and whisker plots. You should memorize the correct way to summarize and display categorical and continuous variables. If you're ever unsure of the best way to present data, go back to the level of measurement for the variables in question and use that as the way to decide how to display it. I might make an extra note. Often you'll see people use pie charts, and pie charts are a little more difficult to judge differences in size just because you're looking at a volume there rather than just straight up bar height. So I typically recommend using bar charts over pie charts for categorical data. Note the differences between bar charts and histograms. Bar charts, like you can see on the left, are used for categorical data. The bars represent different categories that are separate from each other. Bars have spaces between them. Histograms are used for continuous data. Bars represent bins, meaning they've kind of picked a range, a low and an upper value to make a bin from. Bin width is determined by the statistical software. Bars have no spaces between them because the values are continuous unless there's no values in that particular bin, like you can see here on the right. Note some common conventions regarding how box plots are constructed using the 5-number summary. Box plots are used for continuous data. They're often constructed using what they call the 5-number summary. That's the minimum, the maximum, the median, the first quartile, and the third quartile. The line in the center usually represents the median. The top and bottom of the box represent the quartiles. The whiskers extend out from the quartiles to the minimum and the maximum. Box plots with outliers are used for continuous data. The line in the center usually represents the median. The top and bottom of the box represent the quartiles. The interquartile range, or IQR, is calculated by finding the difference between Q1 and Q3. The whiskers extend out from the quartiles 1.5 times the IQR. Values in the data that exceed 1.5 times the IQR are shown as separate points on the box plot. So just be aware that sometimes some box plots can be constructed using slightly different rules. I typically prefer to see these ones that are denote outliers and use the IQR as the range of the whiskers. That's what you're typically going to see in statistical software. The two common measures of central tendency are the median and the mean. The median can be used for ordinal, interval, and ratio data. often used when data are skewed. The median is calculated by arranging data from smallest to largest values and finding the midpoint. If the number of data points is odd, the median is the middle value. If the number of data points is even, the median is the average of the two middle values. The mean is used for continuous data, interval, and ratio. It's commonly known as the average, which we all grew up learning in school. Primarily used when data are normally distributed, we have large sample size, and we lack significant outliers. Sum all values and divide by the total number of values to get the mean. The two most common measures of spread are the range and the standard deviation. The range can be used for ordinal, interval, and ratio data. The range is often used when the data are skewed. It's calculated by finding the distance between the minimum value and the maximum value. The standard deviation is used for continuous data, interval, and ratio. It's primarily used when data are normally distributed, you have large sample sizes, and you lack significant outliers. The formula is slightly different for the population versus the sample. This is the sample standard deviation formula with n-1 on the bottom. The average distance, the values in the distribution are from the center point, is what the mean is telling you. Many variables in natural and social sciences follow the normal distribution. It's also called the bell curve. It's symmetrical. The mean, median, and mode are all equal. 68% of values fall within one standard deviation. 95% values fall within two standard deviations. And as you can see on the figure, 99.7% fall within three standard deviations. Be able to identify asymmetric, positively and negatively skewed distributions. The positively skewed distribution is right skewed. You can see this on the left. I guess I should have maybe switched them, but outliers are positive. Outliers are to the right of the mean, and the mean is greater than the median. The outliers always pull the mean towards themselves, so that's the direction that they'll go. Negatively skewed is left skewed. Skew is described in relation to the tail. Outliers are negative. Outliers are to the left of the mean, and the mean is less than the median. So the way I try to remember positive and negative is like the picture of a rat, and think of the body and then the tail. And the direction of the skew is always in the direction of the tail. So on our blue figure here, that's positively skewed. That's right skewed. The tail is going off to the right. On our pink example, it's negatively skewed. It's left skewed, and the tail is going off to the left. So I don't know if it helps. Think of a rat and which direction the tail's going. The outliers are in the direction of the tail. That's the direction. And then you want to be able to identify kurtotic and leptokurtic and platykurtic distributions. Leptokurtic are tall and skinny. That basically means positive kurtosis. And the way I always remembered that is leaping over a tall building. So you leap to get over a leptokurtic distribution. Platykurtic is wide and flat. That is negative kurtosis. And think of a platypus. Platy means flat, and platypus are pretty flat little animals, and so they're shorter and wider is a platykurtic distribution. So a regular normal distribution would be called a mesokurtic distribution. So z-scores are useful for identifying outliers. Z-scores are measured in standard deviations. A z is a standard score. And x is the observed value, the mu is the sample mean, and the sigma is the sample standard deviation for the formula on the left-hand side there. Z-scores around 3 or greater are typically considered outliers. So we have our normal distribution with our 68, 95, 99.7 rule, and 99.7% of the data falls within 3 standard deviations. So 3 is definitely an outlier. Between 2 and 3, you're starting to push push the limits there, you know, should pay attention, but once you hit 3, you're definitely in outlier territory. Z-scores are useful for comparing variables with different units. Since z-scores are measured in standard deviations, the original units of measure fall out of the equation. And so on the top of there, x and mu are going to have a unit, and then you're dividing by the standard deviation with the same unit, and so those units will cancel each other out, and so there's no units in a z-score. Variables with different units of measure can be compared with each other using the z-scores. Z-scores around 0 lie close to the mean. Positive z-scores are above the mean. Negative z-scores are below the mean. And this is really useful for things like psychometric instruments, like anxiety and depression. Because they're measuring different things, you can't really just take the raw scores and compare them to each other. A score of 10 on a depression questionnaire is not going to be the same as a score of 10 on an anxiety questionnaire, but you can convert both of those to z-scores, and then you can compare those standardized scores to each other. So z-scores are a really handy thing to know about and to use when you're working with different units of measure for things. And looks like that's the end of this one. We'll talk to you later.